Hi, my name is Tully Foote. I'm from the open source Robotics. My name is Tully Foote. I'm from the Open Source Robotics Foundation, and I'm the ROS platform manager. So I oversee the worldwide ROS community. I want to tell you a little bit about it. I'm going to start out talking about the motivation, why we actually got involved, started ROS, and have been working on it from the beginning. I'm going to talk about what's going on right now at the Open Source Robotics Foundation and what the state of art in ROS is. Talk a little bit about our future plans, and also talk to you about how you can get involved. It's an open source project, BSD license. Most of the core code is now on GitHub. Go there, you can fork it, and I'll link to how to get to the tutorials, etc. So starting with the motivation, I'll give you a little bit of my personal background. In college, I worked on all the DARPA grand challenges. You heard Rich talking a little bit earlier about the DARPA Robotics Challenge. These are the precursor challenges that DARPA did, doing autonomous driving. How many are you familiar with this? Okay. So the challenge overall was to get cars to drive autonomously. The first two versions were in the desert. The third version was in an urban-like environment. The first vehicle I worked on was Bob. It's a Chevy Tahoe. We stripped it out. We had metal racks in the back with 8 computers, bungee corded down, UPS and a generator built in. And we drove about 1 mile in the competition. We were the seventh farthest, I think, of the entire competition. And nobody was able to get anywhere near the 100 miles that DARPA asked for. A couple years later, round 2, at Caltech, we had another vehicle. This one was named Alice. Big Ford E350 van. We upgraded from computers bungee cord to racks to actually being rack mount computers. And we had coding consoles in the back of there. And a great platform. And we were able to get farther, not quite there. I've got a video of that in a little bit. And the last one was the urban challenge. And so DARPA had been successful getting people to drive through the desert, following trails and dirt roads. And they wanted to step it up a level and say, okay, now we want to be able to do it with more and more vehicles and have them on the course at the same time. In the first two, there was no vehicles interacting with other vehicles that were actively driving. So this is a picture of Little Ben, the car I worked on at University of Pennsylvania. And a lot of this work has been gone on, and it's now, you can see it in things like the Google Autonomous Driving Project. A lot of the people who worked on this DARPA challenges are now there at Google. So these are 2 vehicles. On the left is the one I worked on the right is the one from Stanford. And I want you to take a look at it and see what about those vehicles is different to you. Because when I look at it, I squint my eyes a little bit. They've got different coloring, but they're basically the same vehicle. They've got the same, all the same sensors, basically the same computers. Almost all the technology inside of those is the same. And we had 100+ teams working for almost 5 years to make this happen. And in that amount of time, we went from cars that could drive a couple miles just avoiding bushes in the desert to cars that can go through with the correct precedence and be able to navigate a rotary, which many humans can't actually do correctly. Yes, and actually I've heard anecdotes of this, that Google and the people that are actually testing cars on the road have actually had to make the cars not follow the rules, but they follow the actual what people do. Because if you follow the rules exactly, you get into deadlocks because people don't actually follow the rules. Actually. So this is our vehicle in the second race. It's the end of the race. If you hear if the audio was on, you'd hear people yelling, scream, watch out, etc. It's one of the most exciting ends to this race. Everyone else failed. It turned out that the part of the course that we went off the side of was the press box. If you go on YouTube, there's another video of the vehicle's eye view of people scattering, and one person doesn't know which way to go. But the point I want to make on this is that we failed because one of our laser sensors went down. And it was just a driver issue. We don't know what happened. We've never seen that error before. We've never seen that error again. We can't reproduce it at all. But one of the lasers stopped reporting. And it happened that the two lasers were tied together so that the other laser would not interfere with the first laser. And then now we're driving half blind. That's 2 out of 4 primary lasers offline. So we had only long range and near range. And then we were going very slowly. We were going through dust. We had issues. We ended up stopping under power lines. And there was, we had lost GPS. So we're sitting under the power lines waiting for GPS to come back. GPS did not come back because we were under the power lines. So we decided to drive again. And in the code that resumed from waiting to reacquire GPS to starting drive again, there was a small coding error which led to a couple degree yaw offset. So we thought we were driving straight down the road, but we're actually veering to the side. And so it's all of these things came together, and that was why we failed. And the point I want to make is that getting these cars to do these things, it's not really about the planning algorithm. It's not about all those things. You have to have all those. But the thing you really need is you need the car to just keep working and do things right consistently. And it's mostly about engineering more than research and development on the super high-level stuff. And you think about that, and you think about all those 100 cars that were in that challenge. If we had all collaborated and used the same open source laser driver, hopefully the bug would have been found by the many more people using it and testing with it. And if you think about all those different vehicles in there, the things that made the difference between the teams that won and the teams that were 1 or 2% behind in the overall elapsed time was not the laser driver. They had laser drivers that worked, and it's just that they had a slightly better algorithm. But if they had been able to use all those resources and share the core base between all those cars, we could have had something like 100 times more progress in 5 years. And I just showed you the difference of a couple years. And if you take this model, you can also look at the research world for robotics. In the academic research world, a lot of what happens is a grad student comes along, he takes a couple years, he builds a robot, he goes out, he does his research on the robot, and then he graduates. And the next grad student comes along, and they want to reproduce it at another university. And the first thing they do is they build a robot. Then they reverse engineer from the paper the other person's research, and then they build on top of it and extend it. And this cycle just keeps going. And it turns out that to get progress, it has a cycle time of several years. Now, if these people had a platform they could build on top of and just incrementally release their stuff on top of it, they could each build on top of each other, and you take the cycle time from years down to days. I'll tell you a little bit more about that, but this graphic is showing that. I mean, these are standard tenets of everything we want to do. We want to reduce, reuse, recycle. Code takes a lot of effort to develop. Robust code takes a lot more effort to develop. We should make use of it more repeatedly and make sure that we don't double expend effort. And so looking at that, on the left you have the open source Linux model, and on the right you have the academics, and what we want to do is we want to marry them together. And from that, we got ROS, the Robot Operating System. And the important things we did with ROS, we sat out, we said we want to make a platform that people will work together on. And to do that, we set out and we said we're going to build a platform to do that. And this is important. Just going out there and leading, you have to have a leader to get a team to go forward. That's what we did. We chose an open source license. In particular, we chose the BSD license. This allows us to both reach out to academic and hobbyists, but also we can get commercial users to come in and say, I'm going to use this on my product and be part of the community. There's no requirement they contribute back, but being a part of the community is actually valuable to the community. The other major effort we've been doing with the ROS project is we've been doing a lot of integration. And I've got the picture of a guy balancing on top of a ball because that's really what our job is like, maintaining the core, where basically everybody's building things, releasing things, and the actual thing that's really valuable to you, the end user, is that it's all put together and you can balance on top of it. And if there's not somebody spending a lot of time actually keeping this thing all upright, balanced, and building, it's not very useful to you. And the final point I'd like to make that has really been valuable to the users is that documentation is critical. You can have a great product, but if nobody knows how to use it, nobody's going to use it. We've put a lot of effort into documentation. Definitely keep that in mind on any project you're on, whether it's open source, closed source, anything. So I'll give you a quick overview of the tools we have, some of the tools we made available. Obviously, we have a build system. We've got 3D visualizers to help you see what the robot's thinking about, and overlaying real sensor data. This is I think a Kinect view with the 3D model of the robot as well as a camera view. We can put in markers, keep track of the history. This gives you just a sense of what the robot's doing. Also, we can look at maps. You can see the 3D rendering of the obstacles above the map. Of course, your simple linear graph is quite valuable. Just being able to look at things in time, introspect what's going on in the system in terms of numbers. And we also have a large logging and playback capability, so you can actually run your robot, collect a log file of all the information that's going on in the robot, and then afterwards you can come back and scrub through it, and you can see the thumbnails of the images, you can plot things over time, find out what actually went wrong, what went right, etc. And also building into this entire ecosystem is that we've been working hard to bring in core open source libraries such as OpenCV, and we've developed PCL, the point cloud library. These are 2D vision and 3D vision algorithm libraries that let you bring in the state-of-the-art research that's being developed in these libraries and released, and just use them. So if you want to do face detection, it's like a couple line call to OpenCV. If you want extraction from point clouds provided by a Kinect, it's also a couple lines in PCL. So with that, we also have I talked a lot about keeping the integration and keeping everything's running. We've been using Jenkins a lot to do continuous integration. We have some tens of thousands of jobs running regularly to keep the entire infrastructure running. For documentation, the most important entry point is ROS.org. It's a wiki. We want everybody to document their things there. So if you want a ROS resource, go to ROS.org and search for the name, what you want, or if you know the name, just go there and browse to the name. And if you have any questions about ROS, answers.ros.org is the place to go. It's a Q&A website like Stack Overflow. In terms of where users are for ROS, snapshot of our analytics for the wiki. You can see we have a large user base in the United States. Europe is also very active. If you sum up all of the European visitors, they actually total close to what the US total is. And also we have penetration all around the world. And if you ask for me later, I can show you a picture of ROS running in Antarctica even. So one of the important things is ROS is being used in a lot of places. It's also being used on a lot of robots. We have a large variety of robots using ROS. We've got big ones like the Carobot and the PRT. There's autonomous cars running ROS. And it goes down to small little robots like the NXT can interact with ROS, or just little servo bots. So we've developed this great software. We want to say, hey, how does this actually work? And we want to be able to show people that it works, not just tell them, oh, this is great stuff. And so at Willow Garage, we put together the PRT, which formed a platform to build on top of. You can find out more specs if you go to willowgarage.com on this. I need to keep going. But PRT is a great platform. We wanted to convince people of that. And how do you do that? How about fetch beer? Pretty common example. So we set out to make the PRT able to go and fetch beer. If you see in this video, we had you order from web form. It goes up to the fridge, opens the door. It's detecting the labels of the bottle using OpenCV and PCL to localize the bottles. Then it'll take it and bring it to you wherever you are. I'll note that this demo was done entirely in a 1-week span. We started Monday morning, and this video was taken Friday afternoon. It was also done as a proof of concept that our development environment was good. So it was the people at Willow saying, we're going to do this hackathon and make it happen. And it'll wait for you to picture there and make sure that you can see, it sees a person before it'll let go. And we were also able to get it to open a bottle. So this wasn't the only hackathon we did. Another hackathon we did, actually I guess it was the week before, was to make it play pool. And so we had the PR2 playing pool. There were no external fiducials. It's localizing itself based on the diamonds on the edge of the table. It's doing blob detection to find the balls. We were very happy when it made the shots. You'll note it makes a bunch of shots in this video edit, but it doesn't make quite the same percentage in the real world. But again, this was a week-long project. We were working late at night. One of the big problems we had was the sunlight in the morning. We tested got all the vision working at night, and then in the morning the sun came up. But it did make some quite impressive shots. So that's what we at Willow can do with the robot. Another question is, what can other people do with the robots? So at Berkeley, when we were developing the PR2, one of the grad students there came down to Willow and used the robot at night to learn to fold towels. And it's great, people loved it, but you can see there's a lot of external implementation, and there's that little number in the corner saying 30x. It was like 10 plus minutes to fold a towel. And the poor guy that was filming it, he tried to do 10 in a row. But you can see a year later they came back and they were able to get it to get a 5x speed up just using the new revision of the software, which has been really great to prove it. And also with the new revision, they're not using any external sensors, etc. So to give you a sense of more of the variety of robots using ROS, this is a compilation. ROS just turned 5 years, and we put this together of people using ROS around the world. There's lots of indoor robots, outdoor robots, fake Mars robots. They're starting to be used for more commercial applications. Also indoor 3D localization, pipes to inspect them, humanoid nows. And of course your standard Japanese floor in the kitchen. And also smaller robots that hobbyists are using. And we've also started getting penetration into the industrial arms, industrial automation, where the ROS tools, integration tools are... Is this thing cutting out? Okay, I'll talk loud. So industrial automation, where these tools are starting to be used for commercial purposes, and the motion planning algorithms can all be just ported into these industrial robots. So I need to keep going here. So talk a little bit about where we're going in the future. We've transitioned, ROS was originally developed at Willow Garage. We've transitioned maintenance of it to the Open Source Robotics Foundation. And one of the main projects that was mentioned earlier is the DARPA Robotics Challenge. It's one of the highest visibility uses of ROS right now. You saw some of the pictures of the larger robots using ROS. And even a lot of the teams were required to use ROS for the simulation, but other teams that are coming in with their own funding, their own sources, are using ROS. And actually the simulator for the simulated challenge, they're verifying their home-built robots. Well, I shouldn't say home-built. They're custom robots inside of the simulator and making sure that everything runs in the simulator before they run it on the real hardware, just to make sure a sanity check. And the simulation is now good enough that you can do dynamically balancing humanoid robots in simulation. And run them with the same walking controller. So looking forward, we've started pushing to get upstream into Ubuntu, and hopefully we'll start extending out into Fedora. Right now we host our own packages on Ubuntu. And there's also ROS Java, which we're releasing Android packages, so you can actually control robots from your phone, just installing an app from the marketplace. So now I've talked about a little bit where we're going. I want to talk about how to get involved. A couple years ago, Melanie and I developed the Turtlebot. Melanie's sitting here with us as well. I'll show you the video. But this is the Turtlebot. We developed it to make a way that people can get involved with robotics. We've been working on the PR2. We've been doing a lot of cool stuff with robots, state-of-the-art technology. But a lot of people would look at it and say, well, I don't have a $400,000 robot. So robots, we had ROS running on the PR2, and we're saying this is our flagship product, and the robot, it's running great, and everyone should use it. But people didn't really have a sense because they didn't have a big PR2 in their, to use themselves. And Mel and I sat down and we're like, well, you know, let's figure out what the minimum required product is to provide this state-of-the-art robotics experience to anyone that can go out and pick up a laptop, basically. And putting that together, we were able to say that the minimum we could come up with was a netbook, an Xbox Kinect, and an iRobot Create. And now you can go out, if you go to turtlebot.com, you can see sources. There's also the source there. It's an open source hardware and an open source software product. So you can go there and actually download designs and build it yourself. There's people in the Homebrew Robotics Club down in Silicon Valley that have done it for, they claim, $200. And the thing I'd like you to think about for the Turtlebot is, what is the difference between a phone and a robot, such as the Turtlebot? They've got APIs, they've got programming, except the robot can actually drive around. So you actually have something that you can interact with the world. It's not just a passive thing that you carry. And as we go forward, start to look for actually having, our term is apps on wheels. They can interact with you in the world, they're autonomous agents. They don't need a person to carry them. And as I mentioned, if you don't want to just jump right into building your own robot, you can download the simulated robot for online and be able to deploy it or test it in simulation before you make the decision to go out and get it, just to make it even more accessible. So I encourage you all to go out to ros.org. If you click on the home page, there's a link to tutorials. It'll show you how to get started. You can install a VM and run ROS there, or you can actually install Ubuntu on your machine. That's the easiest way to go. So